Analysis of any power converter involves, first of all, understanding the basic operating principles by looking at the equivalent circuits valid in different intervals of operation of the converter. Then using the steady state, DC steady state principles to derive the input-output relationships and a thorough understanding of the various current and voltage waveforms within the converter. So in this video, we will look at the analysis of a boost or a step-up DC-DC converter, and we'll also look at the average model of a boost converter. And if you have already reviewed the video on average modeling of a power pole, then you'll be able to follow the average model analysis fairly easily. The figure shows the schematic of a buck converter, which you have analyzed in detail in a previous video. So in this configuration, the power flow is from this VIN to the VO, essentially from the high voltage side to the low voltage side. So this is the direction of the power flow. Now the same circuit configuration, essentially this bipositional switch and this inductor. So if this configuration, as suggested by this animation, if you flip it left to right, then that gives us the circuit configuration for a boost converter. So essentially this side becomes the new input for the boost converter, the low voltage side, and the side where the two portions of the switch is connected, that becomes the output with the output filter capacitor and the load resistance. So in this configuration, power flow is from the low voltage side to the high voltage side, and this is the boost converter configuration. Now this is the complete schematic of a boost or step-up converter with the correct switch realization of the power pole shown. Now as indicated here, this schematic corresponds to unidirectional power flow. Essentially the power flow is constrained to be this defined input side VIN to the defined high voltage output side. Or in other words, the inductor current as defined here is always, IL is always greater than or equal to 0. So for this application, we can implement the bipositional switch just by a single MOSFET and a diode combination. The MOSFET or the switch S1, this is switched at high frequencies as indicated by its gate array waveform Q sub A. So Q of 1 means the switch is on, and this interval is the DTS period. So essentially D, the duty ratio, is defined as the ratio of the on interval, T on, when the switch is on, over the complete switching period TS. So that's the duty ratio. And during this interval, the current in the inductor and therefore the energy in the inductor builds up, and when the switch is turned off, this energy is released to the output side through the diode D1. So the turn off period when the diode conducts is the 1 minus D times TS interval. The boost converter, as the name suggests, is used for applications where the output voltage always needs to be higher than the input voltage. Now the exact mechanism by which we get higher output voltage, that's something that we will learn in the following slides using the equivalent circuit analysis. The two distinct intervals of operation for a boost converter are shown here. The first is this DTS period when the switch S1 is on. So I'll call this as the on interval. And the second one of duration 1 minus D times TS. This is when the switch S1 is off. So I'll call this as the off interval. Now I should also qualify this by saying that these are the two distinct intervals in the CCM mode of operation. So for this operating condition, if you look at the on interval, that is when the switch S1 is on, therefore this end of the inductor is shorted to the ground by the switch S1. So again, if you look at the left hand side of this circuit, the voltage across the inductor as defined as this polarity is positive VN. And again, because of this positive voltage, the current IL as defined as with this polarity increases, and therefore the energy stored in the inductor also increases during the on interval. Now this is going to be fed to the load in the next sub interval. But during the on interval again, if you look at this part of the circuit, we can first of all establish that the diode D1 will be reverse biased. So for example, the point A is connected to the ground by the switch S1. Therefore the voltage across the diode is the complete output voltage VO, and that reverse biases the diode, so it is off. So that is represented by this open circuit here. And during this on interval, the output capacitor supports the entire load current, and therefore it begins to discharge. Now the C is chosen large enough such that as it supports the entire load current, the reduction in the output voltage is very small during that on interval, or the high frequency ripple is very small. Now looking at the off interval, so this is when S1 is turned off, and because of the current in the inductor, the diode D1 would be forward biased. Essentially the inductor current would force a path through the diode D1, and therefore the switch S1 is now open circuited and the diode D is now shorted. So the L is now directly connected to this output capacitor load combination. Again, looking at this circuit, we can see that the voltage VL across the inductor is now Vin minus VO, and so this is where the why this behaves as a boost converter. Now we know that in steady state the current in the inductor should come back to its original value, which means we need the for the current to decrease, we need the voltage across the inductor to be negative, and the voltage is Vin minus VO. Therefore VO has to be higher than Vin for VL to be negative and for the converter to reach steady state. So during this interval, the voltage across the inductor is negative, therefore the current decreases. The energy which was stored in the inductor in the previous cycle is now fed to the load and partly to the output capacitor. Capacitor current is now positive. It is the IL. So this is IL and this would be IO. So IL minus IO is a positive current going into the capacitor, and that charges the capacitor. Once again, we assume that the capacitance is large enough such that this positive current, the voltage rise due to this positive current is very small, resulting in very small high frequency ripple. Next, let's derive the input-output voltage relationship for a boost converter using the basic steady-state analysis principles of switch mode power converter. So we can start by applying KVL around this loop. So essentially it says that KVL in an average sense. So we get Vin equals this VL average, VL bar, plus this is VA, so it's VA bar. So that is the average KVL around this input side loop. Now in DC steady state, the average voltage across the inductor VL bar is 0 in steady state. Therefore we get this equation that VA bar, the average voltage of this pole A with respect to the ground, is equal to Vin in steady state. Now let's look at the instantaneous waveform of this pole voltage V sub A, and so this is the gate drive signal for S1. So when Q is 1, or when the switch is on, the V sub A is, which is simply the voltage across the switch. So when the switch is on, this is a short circuit, VA is 0. Now when the switch turns off or Q is 0, then we know that the inductor current forces the diode D1 to conduct. So at that instant, A is tied to the output voltage. So this voltage with respect to the ground is VO. That is what is indicated here. Now if you obtain the average value of this V sub A, that would be 1 minus D times VO. Essentially it is 0 for this entire DTS period, and it has a finite value only during the 1 minus DTS period, and that finite value is VO. Therefore the average is 1 minus D times VO. Now, so VA bar we have derived from the waveform is equal to 1 minus D times VO. And comparing these two equations, we see that Vin equals 1 minus D times VO, or the required input-output relationship is that VO over Vn, the output voltage divided by the input voltage, is equal to 1 over 1 minus D, where D is the DD ratio as defined with respect to the switch S1. Again, you can see from this equation that first of all, the valid operating range for D is 0 to 1. So for any values of D between 0 and 1, we can see that VO is always higher than the input voltage, and that's why this is a boost converter under all operating conditions. This is the plot of the output voltage, or the ratio of output voltage to the input VO over Vn as a function of the duty ratio D. Essentially, this is the plot of 1 over 1 minus D as indicated here. So this is the ideal waveform, and for example, when D equals 0, then VO equals Vn, or VO over Vn equals 1, and as D increases, this ratio keeps increasing. And theoretically, under assumption of all ideal components, then when D equals 1, we should get infinite output voltage. But in practice, when we consider the non-idealities, especially the resistances of the inductor and the on-state resistance of the MOSFET, and the voltage drop across the diode, when we consider these non-idealities, then the input-output relationship is going to be significantly different. So for example, this red waveform is the VO over Vn as a function of D, considering the resistances of the inductor and the MOSFET. I think in this example I consider the losses in these resistances to be about 0.5% of the total power of the output power, a typical value. So we can see that for this typical condition, the VO over Vn is no more than about 7. So it is very difficult to get large conversion ratios above greater than 10. It's very difficult to achieve, even if we can make the resistance of the L extremely small. And this effect of the deviation from the ideal VO over Vn relationship is dominant for high values of duty ratio. And in particular, when we do reach D of 1, there is no power transfer at all, and the output voltage is exactly equal to 0 for D equals 1. So if we do need very large conversion ratios, then one option is to have multiple stages of this boost configuration, or go for isolated and other topologies. Now we are in a position to draw the various current and voltage waveforms of the boost converter. Now this will help us in a thorough understanding of how exactly the boost converter operates, as well as lead us into the design methods for designing various power stage components. Now to draw the different waveforms, we make use of these two equivalent circuits valid during the on interval and during the off interval separately. So the first waveform is that of the gate array waveform Q sub A. When Q is 1, the switch is on, and Q is 0, switch is off. And they define the DTS and the 1 minus DTS period respectively, intervals respectively. Then the pole voltage waveform V sub A with respect to the ground as defined here. This would be same as the switch waveform, and we have seen this waveform in the previous slide. So this switches between 0 when the switch is on to the output voltage VO when the switch is off and the diode is conducting. So here we implicitly make use of this small ripple approximation, which essentially says that the VO of T instantaneously is equal to VO, and that neglects a small high frequency ripple. So that is why we were able to draw this part of VA waveform to be a flat line of value equal to VO. The average of Q sub A is by definition the D, and the average of V sub A, once again we derived earlier, is 1 minus D times VO. Just essentially take the average of this over one complete period. The next waveform we see is that of the inductor voltage V sub L. So during the on interval, looking at this equivalent circuit, VL is exactly equal to Vn. VL is defined with this polarity, and that is what is indicated here. And during the off interval, we look at the second equivalent circuit, and here VL is Vn on one side minus VO on the other side, so it's Vn minus VO. And for a boost, VO is higher than Vn, therefore this is a negative quantity during the off interval. Now we know that in steady state, VL bar for any converter should be equal to 0. Therefore, the area under the positive portion of the waveform, denoted by this yellow rectangle, is exactly equal to the area under the negative part of the waveform, and these two areas are equal to result in VL bar equals 0. Now we can use this waveform of the inductor voltage to draw the inductor current waveform, and the inductor current is simply the integral of the voltage over L, and so the slope during the on interval is denoted by M1 is equal to Vin over L, and the slope during the off interval is Vn minus Vo over L, a negative slope. So now this gives the wave shape of the inductor current, but we still need to know either the starting value or the average value to draw the unique waveform of the inductor current given this inductor voltage waveform. Now to get the average current, we see that the inductor is connected directly in series with the input. Therefore the average inductor current IL bar is exactly same as the input current IN, and that in terms of the load current is given by this expression. Essentially this comes from the power balance, which states that under steady state, neglecting our losses, Vin times In equals Vo times Ivo. Therefore In is Vo over Vn times Ivo, but Vo over Vn is nothing but 1 over 1 minus d. Therefore In is Ivo over 1 minus d. So that is the average value of the inductor current. So once we know this average and the slopes, then we have the complete wave shape, complete waveform for the inductor current. Now, even though we have already derived the input-output relationship, we can also use the volt-second balance across the inductor to again derive the Vo over Vn. In many other converters, it is probably easier to apply the volt-second balance to derive the Vo over Vn relationship. So let's apply that for the boost converter case. So essentially we have to look at the inductor voltage waveform. During the on interval of duration dts, the magnitude is Vn. During the off interval of duration 1 minus d times ts, the magnitude is Vn, it's Vn minus Vo. So the sum of these two, which is the average of VL over one complete period, that is equal to 0 by definition of steady state. So again, collect all the Vn terms together and Vo terms separately. Then we get the relationship Vo over Vn equals 1 over 1 minus d, which is exactly what we derived in the previous slide. Next, we will focus on the output side, especially the current through the diode D1 and this capacitor current I sub C. Now to draw the diode current, we realize that the diode current is exactly same as the inductor current when the switch is off. So when the switch is on, there is no diode current, the diode is reverse biased. So during the on interval, ID is 0, and during the off interval, it's exactly same as the inductor current, and goes back to 0 at the start of the next switching period. So that's the instantaneous I sub d. What is its average value? To get the average value, we can apply the average KCL at the node that I've defined as x. So at this node, the average KCL would be I sub d, ID bar is equal to IC bar plus IO bar, or simply IO because there is a DC quantity using our small ripple approximation. And in DC steady state, we know that the average capacitor current is 0, therefore IC bar is 0, resulting in ID average to be exactly the load current, and that is shown on the plot as this dotted line, which is ID bar, and that is equal to the load current IO. Next, we will look at the capacitor current I sub C. To get the instantaneous capacitor current, Again, we can use KCL at the node X, but in an instantaneous sense. So instantaneously, IC is ID minus IO by KCL. Therefore, once we have the waveform of I sub D, just instantaneously, point by point, subtract the load current IO, then we get the capacitor current I sub C, and that is shown here. So this is essentially the I sub D with its average value of IO removed to give I sub C. So during the on interval, IC is exactly equal to minus IO, because when the switch is on, diode is off, the entire load current is supported by the capacitor, and for the assigned direction of I sub C, it is a negative discharging current, and that's why it is negative value here. And during the off interval, when the diode conducts, the current here would be this entire IL minus the load current. So that is this waveform. This portion here is really IL minus IO. Once again, in steady state, IC average should be 0. Therefore, the area under this positive portion should be exactly equal to the area under this negative portion. These two areas are equal, okay, such that IC bar is exactly equal to 0. Finally, we will look at the average model of the boost converter. In a previous video, we derived the average model of a switching power pole to be an ideal transformer with its turns ratio equal to the instantaneous duty ratio of the power pole. We can apply that for the boost converter also, but there is a small difference only for the boost converter. So that is related to the way that we define the duty ratio. In all the converters, the D's, let me use uppercase, the D defined with respect to the switch is exactly equal to the D defined with respect to the pole. But only in boost, the D switch is really 1 minus the D pole. Okay, so that is because in all the other converters, when the switch is on, that connects the positive of the voltage port voltage to the pole A, whereas only in the boost converter, when the switch is on, it connects the pole to 0 and not to the positive end of VVP. Therefore, we have to define the D switch to be 1 minus D pole, and in the turns ratio for this ideal transformer, we should use 1 minus D instead of D. Now, with that clarification, here is the complete average model of a boost converter. So essentially, the switch diode combination has been replaced by an ideal transformer with its primary connected to the voltage port with the turns of 1, and the secondary connected to the current port with the turns of 1 minus D, as opposed to D in all the other converters. Other elements such as the L and C and R, they have been retained as they are in the full average model. The average model is valid for both steady state analysis as well as transient analysis. In fact, it is the transient analysis leading to the controller design which really makes use of the power of the average model. But in this video, we will look at some steady state analysis to show the equivalence of these two models for the steady state analysis. So for example, we can derive the VO over V in relationship using this model. So look at the current port side by applying KVL around this loop. So we have Vn equals VL bar plus VCP bar, but VL bar is 0 in steady state for any converter, and VCP, therefore Vn equals VCP bar, but by transformer action, VCP bar is nothing but 1 minus D times VVP, and VVP is VO. Therefore, VCP bar is 1 minus D times VO, leading to the well-known expression V over Vn equals 1 over 1 minus D. Similarly, we can also derive the current relationship between the input and the output So for that, we'll start with this primary side current. So the current, if we define IC like this, so this is IC bar. So the current leaving the secondary is IC bar plus IO, as shown here, and that divided by 1 minus D is the current entering the winding here, which is same as IN. So IN is IO plus IC bar over 1 minus D. In steady state, IC bar is 0, leading to IN equal to IO over 1 minus D. Again, exactly the same as what we derived earlier from the switch model. Now we can also think of further simplification to get the DC steady state average model. So this is valid only in DC steady state, where we can replace by the inductors by a short circuit and the capacitors by an open circuit. So that results in this DC steady state model from the full average model. So the L has been shorted and the capacitor has been opened. Now it is probably easier to derive these two relationships directly from the steady state average model. In fact, in the plots that I showed for the considering the non-ideality, especially, I considered the series resistance of this inductance. So in the DC steady state model, even though the inductor is a short, we still have the resistance of the inductor, and we can also refer this load resistance to the secondary side. Then it is very easy to show the VO over VN relationships considering the non-idealities, and that's what I showed in one of the previous slides.